Hello and welcome. We have recently completed our introduction to the limit process and used it in the application of defining the derivative of a function. We even talked about how we can define higher derivatives, that is, the second derivative, third derivative, etc., and saw some applications such as velocity and acceleration. In this next section of the course, we'll be diving very deep into the derivatives as functions. We'll be finding formulaically processes to determine the derivatives of different families of functions, such as here we'll be starting with power functions and the natural exponential function. And we'll be doing so to avoid having to use the limit process, because it's quite time-consuming to do the limit, I'm sure you realized, and it's quite algebra heavy. So if we can find some rules to help guide us in the patterns that we find when we do the derivative process by a limit, we can then start applying those rules to the families to which they apply. So we're going to be starting here by taking a look into two families of functions, and really the first family that we're going to look at is much larger than just the polynomial family. Now, Dr. Stewart titles this section Derivatives of Polynomial and Exponential Functions, which it is an introduction to both of those, and it goes further, though, than polynomial. In fact, we'll be taking a look at now of the derivatives of what are called power functions, and power functions would be the product of a real number called the coefficient and in a single term with a variable that is to the power or an exponent that is a real number. So whereas if we're talking about only polynomials would imply that the exponent is only a whole number, right? So polynomial examples would be things like, even x to the 0, x to the 1, or an x to the second, and x to the third. And then polynomial functions will be made up out of adding these together and then putting coefficients in front. So making combinations like 3x plus 5x squared minus 2, for instance. That would be a polynomial. But all the exponents are whole numbers here. Okay. We want to be able to, we're actually going to be able to apply the rule for polynomial derivatives to, in fact, all power functions. That is, a power function would be, if we take a single term that is the product of some real number, okay, the variable to some power, where that power, in this case n, is a real number. So that means that we could be considering the derivatives of expressions like 3 times the square root of x, because that can be written as 3x to the 1/2 power. So it's no longer polynomial. We could also be considering derivatives of things like, how about -2 over x? That can be written as the power function -2x to the -1. All right, so these are examples of power functions here. They're not polynomial, but we can write them in this way so that we can apply what is called the general power rule in order to find the derivatives of these more efficiently, that is, more quickly than we would be able to by applying the limit process. Now we're going to, in this section, take a look at how the limit process actually leads to results that can tell us that the general power rule even applies in cases like this. Okay, but the general power rule, as written here, is only really going to apply when we have power functions, as stated here. The variable is in the base. Okay, the exponent is a constant, and the exponent is a real number here. Now, compare that. Okay, compare that to. Okay, I'll draw a line here. Let's see, connecting. These are two examples right here. Okay, compare that to an exponential function. An exponential function is one where the base is the constant and the exponent is the variable. So a true exponential function would be something like y is equal to a to the x, right, where the exponent is the variable. The general power rule, as we'll be able to see by running the limit, the general power rule does not apply to exponential functions. That is, we'll see in the general power rule, the way we can take the derivative is we move the power, right, the exponent, when it is a real number, we move it to the front, and then we subtract 1 from the exponent, and that's how we find the derivative. And we'll see why that is shortly here. But that is not the way to take the derivative of an exponential function. In fact, the exponential function, as it turns out, is always going to be proportional to its own derivative, and we'll see that. But really, there's only one exponential function that we're actually going to look at the derivative of here today. We'll take a look at the rest of the exponential functions in a later section. Okay, we need to do some more work before we're ready to actually define the derivative of all exponential functions. But in this section here, we will be able to define the derivative of the natural exponential function. Okay, and only the natural exponential function. The natural exponential function is the one with the natural base e, so y equals e to the x. And we'll see that it turns out that the derivative of e to the x is e to the x. It's a really nice one. It's really easy to recall that one. It's a really nice property for us. So you're going to want to make sure that you know that this is the way you find the derivative of e to the x. And we're going to want to know that this is how you find the derivative when you're dealing with a power function. And again, I want to emphasize that the power function, it is the base that is the variable, and the exponent is constant. Switch those around for exponential. And in exponential function, the base is a constant, and it is the exponent that is variable. They have different rules. They belong to different families, and they end up with different rules of differentiation. We also have the constant multiple rule. This is really just a result of a law of limits. We recall before that we already had, okay, for the limit. Okay, if we take the limit, let's say, of x approaches a of c, okay, f of x, okay, we already had that we can factor out the c from that. The limit as x goes to a of f of x. Okay, remember that, of course, when we're taking the derivative, we are really applying a limit, right? So, for instance, if we were to apply the limit, let's say, as x goes to a of the difference quotient here, that would be like c f of x minus c f of a over x minus a. Now that would be a derivative right there, right? That would be our derivative of c f of x with respect to x. Okay, by one of the definitions that we have. Well, we have a constant here in the numerator that is a factor of the numerator, and we are applying a limit, so we are allowed to factor out the constant by the limit law that says we can factor out a constant. So we end up being able to rewrite the limit in this way. All right, and so that means we end up with c times this limit, but that limit, if the derivative exists, that limit is just going to be f prime of a in this case. Okay, in a more general sense, okay, it's going to be f prime of x, right? If we changed it, so we made this the limit as what, u goes to x of f of u minus f of x over u minus x, or we use the other limit definition with the x plus h, okay, f of x plus h minus f of x over h, and take the limit as h goes to 0. Same thing. Just demonstrating here, okay, demonstrating here that this is a proof for why we can factor out any constant, okay, any constant that is being multiplied by a function that we're going to be differentiating. Okay, the sum rule and the difference rule are similar to this constant multiple rule in that we have limit laws that tell us that this works. Again, the derivative is a limit, and we recall that the limit of a sum, okay, and the limit of a difference is the same as the sum of the limits and the difference of the limits. In other words, we can distribute the limit operator. So if we had something like the limit as x goes to a of f of x minus g of x, for instance, we already have established from limit laws that this is the same as the limit as x goes to a of f of x minus the limit as x goes to a of g of x. And this is true, okay, if each limit exists. Okay. Just as up here, right, this statement here was true, okay, if f prime of a in fact exists. okay, as that limit. Okay, so we're really just saying that we are, since the derivative is, a limit process, when we take the derivative of, let's say, a difference or a sum, all right, do this on a sum, we can do it on difference, okay, the derivative of a sum, well, then we can think of, like, okay, limit as h goes to 0, okay, and then we can have our whole f of x plus h minus f of x over h plus g of x plus h minus g of x over h, and we are really saying that we are then distributing the limit. Okay, so the limit as h goes to 0, okay, of f of x plus h minus f of x over h plus the limit as h goes to 0 of g of x plus h minus g of x over h. So in other words, we have that the differential operator, okay, that is the d over dx, right? The differential operator gets distributed, okay, in a linear fashion. So we have the derivative of f plus the derivative of g. Okay. So the sum rule and the difference rule both say that we can essentially distribute the differential operator when we have a sum or a difference. Okay. Now, in the next section that we move into after this one, in 3.2, we'll look at the derivative of a product. The derivative of a product does not work as just the product of derivatives, but we'll get there when we get there. In this section, though, if we have a product, we would want to algebraically expand the product in order to then apply the differential operator. And we'll see that we'll take a look at least one example here today where that is true, and you'll see some in the homework as well. Now, I've provided for you with this section typed up notes. You can consider this maybe an outline, what it would look like in a lot of ways if I were writing this section in a textbook without diagrams and other visual features. Okay, but you can review these notes to see some of the proofs and some examples written out for your benefit. Okay, and so a lot of that information is contained here, and I'm not going to go through this line by line. I really just I want to do some examples here today to help you out with the homework, but I give you a lot of background information here. Starting with, how do we know that the general power rule is actually what it says it is? That is that when you have a power function, if you take the derivative of that power function, okay, how do we know that we can just move the exponent to the front and then subtract 1 from the exponent? Okay, so I want to demonstrate that here by the virtue of first a few examples. Okay, by applying the limit definition of the derivative, okay, in a few examples. Okay, so let's just call this won't be a straight up proof. In fact, the proof for the general power rule, okay, well, there's one proof that you can see in the notes, and it's quite heavy on the algebra, and we'll take a look at it in a moment. But the proof that is less heavy on the algebra and relies more on the brevity of calculus, we'll take a look at in a few sections when we deal with logarithms and their derivatives, so-called logarithmic differentiation, and then we'll be able to prove the general power rule is true for all power functions. But in this section, it'll be sufficient for us to demonstrate that it has to be true for polynomials, and then some other examples that we can work with, like these examples here, for instance, that it also will apply to. Okay, so the actual proof, I'll make a note here, Okay, another proof of this one, other than the one that I give you in the notes, okay, can be found in the section on logarithmic differentiation. Logarithmic differentiation. Okay. That's in a few sections. I believe section 3.6 is where it is in this textbook. All right. But here I just want to demonstrate that if f of x equals x to the n, if f of x equals x to the n, that is a power function, okay, then f prime of x is equal to nx to the n minus 1, and we call this the general power rule. Okay. Let's take a look at the notes here. The case where n is equal to 0, that is, if we have the function x to the n where n is 0 now, okay, well, that's x to the 0. In other words, f of x is equal to 1, just the constant 1. Okay. Well, then by one of the limit definitions for the derivative, the limit as h goes to 0 of f of x plus h minus f of x over h, okay, since f of x is equal to the constant 1, then f of x plus h is 1, and f of x is 1, so we get the limit as h goes to 0 of 1 minus 1 over h, which is the same as the limit as h goes to 0 of 0 over h. Now, when we run the limit, if we try to plug in 0 for the denominator, it looks like we get indeterminate, 0 over 0. But in fact, it is not indeterminate because the numerator is not approaching 0. The numerator just is 0. And remember, when we're running the limit, we're not actually choosing h to be 0. Okay? The idea in the theory here is that we're choosing h to be very, very close to 0. Both positive and negative numbers very, very close to 0. So we actually have what is a 0 in the numerator divided by a number that really isn't actually 0. And as a result of that, this is going to equal 0 then. That is, the derivative of 1 is equal to 0. Now that's actually also going to be true for any constant c. Now you take a look at the worksheet I provide for you. The first thing I have for you to do, this would be an in-class task for you to do, is to take the constant function f of x is equal to c, where c can be any constant, okay, and find the derivative of that function. What is the derivative of f of x is equal to c? Okay, well, let me take an example here. Let's say we have f of x is equal to, how about f of x is equal to 3 squared? I'm going to start with that one. If f of x is equal to 3 squared, notice that that's the same as just saying that f of x is equal to 9. Okay, let's take a look at this one geometrically now for a second. Okay. What does this function look like in its graph? Well, it is going to just be a horizontal line, okay, a horizontal line with the equation y equals 9, right? So for instance, it goes through points like 0, 9, okay? But it also goes through points like, negative 1, 9. And it would go through points like, 9, 9, for example, right? It's a horizontal line. And the derivative of this should represent geometrically the slope of the tangent line to this. That is, the tangent line to this curve at any point should have the same, should share the same point as the curve and be in the same direction as the curve. So any tangent line that we affix to this curve right here should have the same slope as this curve. And what is the slope of this curve? Okay, well, it's a line, and the slope is equal to 0. So we expect that f prime of x is therefore going to equal 0. Right? That would be the slope of the tangent line. Now let's show that by the limit definition. So f prime of x, no matter what value of x we plug in now, right? So this is to say, as a complete function, no matter what x we plug in, that's all real numbers in this case, okay, the derivative is going to equal 0. Well, the definition, the limit definition, is the limit as h goes to 0 of f of x plus h minus f of x over h, okay? Which in this case is what? Well, if f of x equals 9, right? If f of x equals 9, right? Then f of x equals 9, and then f of x plus h would also equal 9, right? Because this is constant. So we get 9 minus 9 over h. And that equals the limit as h goes to 0 of 0 over h. And again, the numerator is always equal to 0. It's exactly 0. the denominator is not exactly 0. It is approaching 0. So when you take 0 and divide it by a number that is not quite 0, you're going to get 0 as the result. So this demonstrates by the limit definition that it is true, right, that the derivative is equal to 0. Now, what does this have to do with the general power rule? Well, we also need the constant multiple in order to fully develop this. Okay. Notice this. F of x, which was equal to 3 squared, is the same as equal to 9, which is the same as 9x to the power of 0. All right? 9x to the power of 0. Well, so that looks like a power function then. Okay, it's a power function. It's of the form y is equal to ax to the power of n, for instance, where n is a real number. In this case, n is equal to 0. So, the derivative of a power function, x to the n, even if we put a constant in front, right, the derivative of ax to the n, first off, by the constant multiple rule, we can factor out the constant a. Right, so that's by the constant multiple rule. And then we can take the derivative of our power function, and that would give us nx to the n minus 1. So we get a times nx to the n minus 1. Let's apply that to our power function here. Okay, so the derivative of 9x to the power of 0, we can factor out the 9, okay, and then take the derivative of x to the 0. Well, that would be what? 0 times x to the 0 minus 1, which is a negative 1. So this, notice, is the product of 9 and 0 and x to the negative 1. Well, that's going to just equal 0 as long as x itself was not equal to 0, right? Because this would be undefined if x was actually equal to 0. Okay? Well, what if x was equal to 0? Let's take a look at that case. We say, well, what if x is equal to 0? Because then it's not proved. In other words, but right now we've just shown that the general power rule is true when we have a constant. Okay? Because we can always write a constant as that constant times x to the 0. We can always do that, and that creates a power function. And then by moving the power 0 to the front of the power function, okay, and then multiplying it, we end up with 0. That's the case as long as the base itself was not 0, because then we would be dividing by 0 then in this expression. Well, what if x was 0? In other words, this rule is undefined right now if x is 0. Well, what if x is equal to 0? Then we define the derivative instead at a point. Okay? Then what we do is we want to find f prime of 0. That is, instead of trying to find f prime of x, the derivative as a function, for this one particular case, we're going to find the derivative at that point because it was a problematic point. Well, what is f prime of 0? So this is the limit as h goes to 0 of f of 0 plus h minus f of 0 over h. Okay, so what does this equal? Well, again, f of x, okay, was already defined to equal 9. So f of 0 plus h, that's equal to 9. So we have the limit as h goes to 0 of 9 minus f of 0, and f of 0 is again 9, and then we have h in the denominator. So we still get limit as h goes to 0 of 0 over h. We get the same conclusion. This is equal to 0. So for sure, okay, the derivative of our function in general, is equal to 0 wherever we happen to look at it within its domain. The general power rule, okay, applies, okay, for any function that is a constant, which geometrically makes sense, right? F of x is equal to a constant will always be a horizontal line, which will always have a slope equal to 0. So the derivative of any constant is equal to 0. So now we don't need to apply the limit definition. If we know we're taking the derivative of a constant, then the derivative of that constant will always just be 0. So now let's take a look at the next case. Well, if n is equal to 1, then the power function f of x equals x to the n would just be x to the 1, f of x equals x. And the derivative defined with a limit, h goes to 0, of f of x plus h minus f of x. Well, if f of x equals x, then f of x plus h is x plus h. And f of x is equal to x, so we get x plus h minus x over h. That gives us h over h. That's just the constant 1. Limit as h goes to 0 of 1 is 1. In other words, okay, the derivative of f of x equals x is just equal to 1. Okay, now let's apply that to another linear function, or even linear functions in general. Okay, find f prime of x if, let's say, f of x is equal to negative 3x, for instance. Okay, well, that's a power function right there. Okay, it's a power function, y equals negative 3x to the first. Okay, and of course the derivative of a power function, okay, ax to the n, okay, we take a out to the front, and then we multiply using the general power rule, nx to the n minus 1. That's the way that's going to work. If we did the limit definition here, okay, we're going to get this result. Okay, we already saw the limit definition works on x. We already know the limit definition works on a constant multiple. We've already demonstrated that. So now let's just apply the rule directly to the power function. Okay, so f prime of x is going to be the derivative of negative 3x. Well, we have a constant, so we use the constant multiple rule. Okay, so we factor out the constant. Okay, and then we have to take the derivative of x, or x to the first, right? So the general power rule says we move the 1 to the front, and then we reduce the exponent by 1. So we get 1 times x to the 0. Right? So there's our general power rule being applied at that stage. And x to the power of 0, well, that's just equal to 1. So this is negative 3 times 1. In other words, it's equal to negative 3. So the function f of x equals negative 3x has derivative equal to negative 3 everywhere within its domain. And that makes geometric sense to us if we were to graph the function. F of x is equal to negative 3x. So negative 3, f of x equals negative 3x would go through points like 0, 0, right? Y equals negative 3x. Or how about if x is negative 1, then y is positive 3. All right, so negative 1 and positive 3, and that would be a point, for example. Okay, so there we go. So a line like so. And of course, we're finding, geometrically, what we're finding with the derivative is the slope of the tangent line. And the slope of our tangent line here is going to be negative 3, as we can see. Right? All right. So increasing n. What happens if we go to where n is equal to 2? Well, apply the limit of the difference quotient to a function like f of x equals x squared then. Okay, something that we've done previously in this course. So by the limit as h goes to 0 definition, we get f of x plus h, which would be x plus h quantity squared, minus f of x, which is x squared. Okay, if we expand our binomial here, we took a look previously at the binomial formula for the expansion of a binomial, right, to a whole number power, is where we had like Pascal's triangle, which gives us an idea of the coefficients we'll get in that expansion, for example, so that we can do the expansion for x plus h to the third, x plus h to the fourth. In fact, x plus h to the power of n for any whole number n. We can do that complete expansion and find all the coefficients. Okay, so we fully expand, we collect the like terms, and then we find that we can factor out an h so that we can remove the discontinuity, then we can run the limit, and what we get is the derivative. Does this apply, or does the general power rule apply if f of x equals x squared? We find, well, yes. We can take the exponent 2, move it to the front, and then subtract 1 from that exponent. That's the general power rule. It will apply to all power functions. Okay. So let's try another example here. We're going to see, We're going to see that it works for x cubed, right? Again, do the binomial expansion here, collect the terms, factor out in the numerator to remove the discontinuity in order to run the limit, right? If the general power rule really works, look at, the time and the effort in the algebra that it saves for us to do the calculus, okay? So there are going to be cases where calculus is going to be the fast route through an exercise. But I'll show you there are also examples where you need to do a little bit of algebra to make the calculus work better. So it's a give and take. You have to put on different hats. Sometimes you need to do some algebra before you do the calculus, and sometimes you need to do the calculus in order to avoid doing a lot of algebra. Okay? This example right here is one where the calculus is very powerful. By doing calculus here, we find the derivative right here. This is the entire derivative process right here with calculus involved. General power rule, and it only takes like basically one quick step and you're done. As opposed to the limit process, which is quite cumbersome, right? Okay, now let's take combinations of some of these, okay? Some of these types of terms and find some more advanced derivatives that we would not want to do with a limit process if we could avoid it. Okay, find f prime of x, okay, if f of x is, let's see, equal to, let's take a polynomial like, how about 5x cubed minus 7x squared plus 1/2 x minus 5. Now, imagine this with a limit definition of a derivative. We got a lot of terms here, we got a lot of expansion going on here, and we could even have worse, exponents than that. Okay, I have this one in standard form, but let's say we even had let's add another term, 2x to the power of 7. Just imagine what it would look like if we had to do 2 times x plus h to the power of 7, notwithstanding we have to do all these other terms as well. The binomial expansion on this alone would be quite expensive in terms of the amount of time we would have to put into this process. So we would not really want to go about it that way. Okay, so the general power rule, because it will apply to each of these terms, and because we can distribute the differential operator, the general power rule saves us a lot of time. So we have f prime of x, which is going to be the derivative of, okay, this entire list of terms. Okay, and we can then distribute the differential operator to the terms. Okay, so I'll just show that here, that's what we're able to do, and that's quite a powerful technique that we can do that. Okay, and again, I want to remind you that if we had a product of expressions, we could not distribute the derivative into that product. So this is not to be taken for granted that we are able to do this for this example. This is really helpful that we can do it in this example. But if we change this example a bit by turning it into a product, we have an issue. We either have to update the calculus, or we have to work with the algebra to make the calculus work better for us. We'll take a look at examples like that. Okay, so we're distributing the differential operator here. And now we have lots of combinations of constant multiple rule and general power rule. So for example, here we take the 5 out. That's constant multiple rule. And then the derivative of x cubed, well, by the general power rule, that would be 3x to the power of 2. All right. Okay, so we have constant multiple rule, general power rule. Constant multiple rule, general power rule. All right, and let's do that again and again. Okay, so take out the constant -7, and then we have the derivative of x squared. Well, that would be 2 times x to the first by the general power rule, or just 2x. Then we factor out the constant 1/2, and then the derivative of x to the first, right, that's going to be 1x to the power of 0, which of course is just going to equal 1. Then we have the derivative of a constant. Okay, recall that the derivative of a constant is equal to 0, right? The slope of the line, y equals -5, that's a horizontal line, that slope would be 0. And then we have For the last term, we can factor out the 2, and without having to do all that x plus h to the power of 7 complete expansion by the binomial theorem or some other type of limit process, we can simply say, well, this is going to be 7x to the power of 6, and that's what we're going to get if we ran the limit. Okay, so a tremendous time saver there. So this term by term shows all of the outputs we would get. You know, when I'm grading an exercise like this, if I were to give you an exercise like this, find the derivative of this function, this is really what I'm looking for in your work, is kind of this step right here, and it shows how you took the derivative of each individual term. Okay, and as opposed to me seeing how you simplified it in the end, because we're focusing right now in this exercise strictly focused on how do you take the derivative. Okay, that's the process of differentiation, as opposed to what is your derivative. Okay, I'm more interested in this example how you're finding the derivative. All right, but this would simplify, like if you were to check the answer in the back of a textbook, you're probably not going to see it looking like this. You're probably going to see an answer that looks like this: 15x squared minus 14x plus 1/2, x to the 0 is 1, right? And then plus 14x to the 6th. In fact, in the back of the book, they would probably have this in standard form. So 14x to the 6th plus 15x squared minus 14x plus 1/2. And what did we find? We just found the derivative. And we did so by using the general power rule and the constant multiple rule, as well as the derivative of a sum and the derivative of a difference. That is, we distributed the differential operator. We applied all those rules so that we were able to completely avoid taking a limit. Okay, so does the general power rule in fact work for all polynomial functions? Well, this answers that question right here. It's very heavy on the algebra style of proof here to show that it does in fact work. One way is to do the binomial expansion on this. Okay, the other way is to use the other definition of the derivative, okay, which I gave you recently as well. The derivative as a function, u approaches x. We have u to the n minus x to the n over u minus x. Okay, and then we can notice, of course, if we were to run the limit here, if we were to take u to approach x and just plug x in for u, we're going to get 0 over 0 in this ratio, of course, the indeterminate form, because both are approaching 0 in the sense of the limit. So then that suggests that we can factor out a u minus x from the numerator. We can factor out u minus x, and if we do factor out u minus x, we will get a list of terms that looks like this. So this proves here that, in fact, the general power rule does apply as long as n is a whole number. That is, as long as we're dealing with a polynomial, it certainly does apply. But what if n is some other real number, not a whole number? That is, what if n is a fraction or a decimal? What if it is a negative number? What if it's an irrational? What if it is any other real number other than whole numbers? Will it still work? And the answer to that ultimately is yes. And we can get an actual proof for that again in a future section when we deal with logarithmic differentiation. But for now, let's just demonstrate by a couple of examples that it does in fact work. So I give you a couple of examples here worked out fully. I give you an example here where you're choosing a negative whole number, that's -2. Take a look at how we can apply the limit definition of the derivative to this function here to show that the power function x to the -2, okay, would actually end up with a result, in this case -2x to the -3, which is exactly what we would expect by the general power rule. That is, the derivative of x to the -2 we can find by moving -2 to the front and then subtracting 1. And it's all demonstrated here by the limit process. Now that we have the general power rule that applies to this family, what we need to do when we want to find a derivative of such a function is first check the family. Make sure that it truly is a power function. That is, that the base is the variable and the exponent is a constant. And if that's the case, you can take the derivative by the general power rule. There would not be a need to do a limit unless asked to do the limit. Now, also ask you on the on the worksheet, I also ask you to do the derivative of 1 over x, which is the same as the derivative of x to the negative 1 power. So here you can check to see what you're going to get by taking the derivative of 1 over x. Does the general power rule actually apply to this example? And the answer to that is yes. But in order to apply it, you first need to write the function. You need to do some algebra here, just one step of algebra. Rewrite the function as a power function in order to apply the general power rule. But what I'm asking you to do in question number 2 is to actually run the limit. Use the definition of the derivative in order to show that you get the result that the general power rule predicts we would get. Okay, so if f of x equals 1 over x, then f prime of x would be what? Well, we have the derivative of 1 over x, but 1 over x is the same as x to the negative 1. That is doing some algebra here, right? We are writing it as a power function before we proceed with the differentiation rule. It would be helpful to note here, you do not take the derivative of 1 divided by the derivative of x. There is no such rule like that. We'll take a look at what the derivative of a quotient is in a future section, but it is not the derivative of the top divided by the derivative of the bottom, as it turns out. Instead, you need to take this step, writing it algebraically as a power function, and then that allows you to apply the general power rule. Okay, general power rule. Okay, so derivative of x to the n is nx to the n minus 1 as long as n is a real number. Okay, so the derivative here would be negative 1x to the negative 2. In other words, another way we could write that is negative 1 over x squared. Okay, so we have applied now the general power rule in order to find this derivative without doing the limit definition. All right, the limit definition, as you would do on your worksheet, is the limit as h goes to 0 of 1 over x plus h minus 1 over x over h. And you need to show that this limit is going to result in negative 1 over x squared. That's what I'm asking you to do on the worksheet exercise, is show that the limit of this difference quotient is negative 1 over x squared, which is the same as negative 1x to the negative 2, and that corresponds to what we would expect to get by applying the general power rule to the function. I'm also asking you to do the limit definition to the square root function. We've done it before. Using that limit definition where h goes to 0, or the other one where as x approaches, or as u approaches x, if you wish. In either case, you're going to get a difference of square roots in the numerator, so you'll need to multiply by the conjugate in order to remove the discontinuity. Okay, but ultimately you're going to find that the derivative of the square root of x, okay, can be found by the general power rule. Okay. If f of x is equal to the square root of x, then what is f prime of x equal to? Apply algebra to this first. Say, well, this can be written as a power function. It can be written as the function f of x equals x to the 1/2. Okay? Write it as a power function first. Then f prime of x is the derivative of x to the 1/2. That's the derivative of a power function. And so we move the exponent to the front, and then we subtract 1 from the exponent, so we get 1/2 x to the negative 1/2, or we can also write that as 1 over 2 root x. And so the derivative of the square root of x is 1 over 2 square root of x. Okay. It would also apply to functions like the cube root of x. Okay. Find out what the derivative of the cube root of x is. Again, use the limit definition of the derivative to find out what it actually is equal to. I demonstrate one like that here in the notes, where I actually do for you on paper here the derivative of x to the 1/4. That is the 4th root of x. Using this limit definition right here, we get a difference of 4th roots. Okay, and now with the difference of 4th roots, we can use this combination right here. Okay. Right, this combination right here, which can verify to be true, you can do that right now. You verify that this is going to be true. Okay. In fact, I showed it up here. Okay. U to the n minus x to the n equals u minus x times this combination of terms right here. It can be shown that that's true by using synthetic division. I'm showing the synthetic division right here, which demonstrates that this property is in fact true for all differences of fourth powers. You can do the same thing for a difference of any whole number power. It can be a to the fifth minus b to the fifth. You would have a minus b times a combination of terms out here. Okay, a to the 12th minus b to the 12th. You'll get an a minus b times a combination of terms out here. And all can be determined by synthetic division. Okay, so I'm showing here what you would get. This is if the case is that a is the fourth root of x plus h, and b is the fourth root of x, well then this numerator is a minus b, right? It's just a minus b. And what I'm finding here is what do you multiply a minus b by? What combination do you multiply that by to get the fourth power of each term? So it's analogous to applying the conjugate. This is the process we used when we had differences of square roots. Okay, I'm showing you how you could do it with a fourth root. Okay, and you'll do the same process with a cube root in order to do this exercise by the limit definition of the derivative. And in the end, what result do we end up attaining? Well, after all that work, all that algebra, we end up with the derivative of x to the 1/4 is 1/4 x to the negative 3/4, okay, which shows up in this form right here, which we write in this form. And notice that does follow the general power rule then. We get the result that says that the 1/4 moves to the front, and then we can subtract 1 from 1/4, which is where we get the negative 3/4. Right? So, more and more, the limit definition is going to be more expensive for us to be able to apply. So, when possible, we want to use the power of the calculus technique in order to eliminate a lot of the algebra that would be there. But that doesn't mean algebra disappears entirely. Again, you have to first rewrite the term as a power term in order to then apply the general power rule. Okay, and that's important. Okay, as I've already mentioned, even in this example right here, if you can't take the derivative of the top and derivative of the bottom, you need to rewrite it as a power term. Then you can apply the general power rule to the entire term. Okay, so now let's apply this new wealth of knowledge to a couple more examples here. Okay, a little more complicated examples where we don't have to do the limit now. Okay, let's say find f prime of t if f of t is equal to t cubed plus 2 over 5t. Well, f prime of t, okay, the Newton notation, then the Leibniz notation, d over dt of t cubed plus 2 over 5t. We cannot take the derivative of the top versus the derivative of the denominator. We cannot do it that way. Okay, it works differently with quotients. So we need to manipulate the expression algebraically. We need to use algebra, okay, in order to separate into terms which are power function terms. So let's say separate into power terms if possible. Okay, so in this case, this is what we could do. They're over a common denominator 5t, so we have t cubed over 5t plus 2 over 5t. Okay. A little more algebra here to simplify. T cubed over 5t is the same as t squared over 5. And 2 over 5t, well, that's the same as, I guess, 2/5 times 1 over t. Write these as power terms now. Well, I noticed one thing. I noticed that I have a 5 in the denominator, and I can factor out the 5. But it's in the denominator, so this is a 1/5, right? So we have 1/5 times the derivative of, and we have t squared, which is a power term, plus 2. And now, writing this as a power term, we have t to the negative 1. Okay, I was able to factor out the 1/5 from both terms, okay, using that constant multiple rule. And now we can use the sum rule. That is, we can distribute the derivative to the terms. So we can take the derivative of t squared, and then separately from that we can take the derivative of 2t to the negative 1. So we have 1/5 times, now the derivative of t squared is 2 times t to the first. That's the general power rule. And then here we have the 2 comes out to the front, okay, constant multiple rule. And then we take the derivative of t to the negative 1, which is negative 1t to the negative 2. Okay, so this step here shows the individual derivatives by the general power rule. And we also used one more instance of a constant multiple here, constant multiple rule. Okay, now if you look up the answer in the textbook or a solution key or something like that, it's most likely not going to look like this. This shows how the answers are found. Okay, but the answer you'll probably find would be maybe more simplified than that. For instance, we can factor out a 2 from both of these terms now, so we can write 2/5 in the front, and then we have a t minus t to the negative 2, so t minus 1 over t squared. Okay, that could be a way that you see it written. Or you could see it as 2/5 times, let's see, common denominator, t cubed minus 1 over t squared. That could be another way that you see it written, for instance. Okay, so this is a more simplified form of the answer. Okay, that does not demonstrate how we found it at all. Right? The demonstration of how we actually found the answer is here in the work. Okay, so it's not just about your answer, but it's about showing the process here in these exercises for how you're finding the answer. All right, let's try another one. So we had here applying a little bit of algebra, and we had a combination of terms. One was a polynomial term, and the other was a rational term that we're able to write as a single power function with a negative exponent. Okay, let's take a look at another example. Find f prime of x this time. You know what? Let's change the name of the function now. How about g prime of x? Okay, we'll do that. If g of x is equal to 5 times the square root of x minus 2 divided by the cube root of x. Alright, so what's the derivative going to look like now? So we have g prime of x is equal to the derivative with respect to x of, let's turn these into power functions here, 5x to the 1/2 minus 2x to what power would this have? That is, what would be the exponent for this power term? Negative 2x to what power? That would be the power negative 1/3. And now we can distribute the differential operator by the difference rule, and then we can use the constant multiple rule here. So we can take out a 5 from the first term, okay, and then we have the derivative of x to the 1/2. And then we take out a negative 2 from the next term, and then we have the derivative of x to the negative 1/3. Now we apply the general power rule. All right, so make a note here. Right, we did the difference or the sum, depending on how you look at it, the sum or the difference rule, okay, and the constant multiple rule as well. Now applying the general power rule, we have 5, switch my color back here, 5 times 1/2 x to the negative 1/2 minus 2 times negative 1/3 x to the subtract 1 from negative 1/3, we get negative 4/3. All right, negative 1/3 minus 1 is negative 4/3, right? Okay, and so this step here shows how we applied the general power rule to finding this derivative. Now, let's clean this up a bit, because the answer we can expect to see in a textbook or a solution key is probably going to be a cleaned up version of this. So this is going to look like, let's see, 5 over 2 square root x. So we can clean that up. And this one over here, we're going to have a plus. We have 2/3, then we have our x in the denominator with a power of 4/3. That can be either written as x to the 4/3, or it could be the cube root of x to the 4th, something like that. Okay, so that would be a possibility. So this might be one way we would expect to see a nice simplified answer. What did we find? We just found the derivative of this function, okay? And we did it without the limit, okay? Without the limit definition, right? And that makes us happy, because by comparison, with the limit definition, this would have been a lot of algebra to have to do here, a lot. Okay, and we've reduced the workload by just doing a little bit of algebra, that is turning these into power functions, getting power terms, okay, or power functions, because a power function is a single term, so it's 2 power functions that we have here. Getting it written as power terms, and then applying the rules, including the general power rule, okay, in order to find the derivative without having to use a limit. So we're able to save a lot of time and effort here, algebraically, through the use of the general power rule when it applies. So some notes. Be sure to understand the limitations. Okay, it works if the function is a power function, but it does not work if your function is not a power function. Okay, so if your function is not of the form x to the n, where the variable is the base, but the exponent is the number, the constant, okay, that's when you can use the power rule. Okay, you can't use it if your exponent is in fact a variable. And we'll take a look at the first of those of such functions where the exponent is in fact the variable here in this section. That is we'll take a look at a to the x, but then we'll focus on what e to the x, its derivative is. And later we'll take a look at the inverses of the exponentials, that is the logarithmic functions. How do we find those derivatives? And shortly we're also going to look at the trigonometric functions, and then the inverse trigonometric functions as well, and some others down the line, the hyperbolic functions as well, which are built off of exponential functions. Okay, we have some work to do up ahead to take a look at these more complicated families of functions. Okay, some more examples for you to look through. Okay, here's a an interesting little challenging exercise here of an application. Find a second degree polynomial that's a quadratic, right? Find a quadratic like this: ax squared plus bx plus c is equal to p of x, such that if you plug 2 into the polynomial, the answer is 5. But if you take the derivative at 2, the answer would be 3. And if the second derivative at 2 is equal to 2, that is a higher derivative there. Okay? How do you take a second derivative? Recall, a second derivative is the derivative of a derivative. Okay? I'm going to give that a try right now. Let's try extending on this. Okay? Well, let's try out a second derivative, and then we'll go back to that other example. Okay? Or I'll finish up the other example, and then I'll come back to this. Now find g double prime of x in this example, right? The second derivative of g is the first derivative of g prime, right? So we're taking now the derivative of this derivative. So that is, we want to have the derivative of this answer right here, and it'll be helpful for us to rewrite it with power terms again. So we'll take 5/2 x to the negative 1/2 plus 2/3 x to the negative 4/3, and then we'll just take the derivative of that. Okay, we'll come right back to that in a moment. Okay, now if your polynomial is second degree, that's quadratic like this, okay, well then we know that if we plug 2 in, we would get p of 2 is equal to 5. Well, if we plug 2 into this expression right here, we're going to get a times 2 squared plus b times 2 plus c. In other words, we're going to get this, 4a plus 2b plus c. When x is equal to 2, that's what we're going to get. And we're being told that's equal to 5. So we get this linear equation here, 4a plus 2b plus c is equal to 5, as a result of evaluating our general second degree polynomial according to this criteria here. Now, find an equation where p prime of 2 is equal to 3. Well, the derivative of this with respect to x, we can find p prime of x. By the general power rule, we would get 2 times ax to the first, so 2ax plus b. And of course, the derivative of the constant c is just 0. So p prime of x is 2ax plus b. Then if we plug 2 in as the value of x, we would get 2 times a times 2 plus b, which is 4a plus b, and that equals 3, according to this criteria. So 4a plus b equals 3 from the first derivative. Now, second derivative, which is the derivative of the derivative. That is, take the derivative of 2ax plus b now. The derivative of this with respect to x, we have a linear term that is x to the first. By the general power rule, the derivative of x to the first is just 1. So we get 2 times a times 1, or 1x to the power of 0, right, which is 1. And the derivative of the constant b is just 0. So the second derivative with respect to x is 2 times a. And we're being told that the second derivative at 2, if we plug 2 in, the answer would be 2. So we plug 2 into this, and so we get 2a is equal to 2. 2a is equal to 2, and that's our third equation. We now have to find the polynomial, okay, the polynomial with specific values of a, b, and c that satisfies this system of equations. These three equations all need to be consistent with respect to some combination a, b, and c. So the third equation we can solve real quickly. A is equal to 1. Plug it into the second equation. A is equal to 1 up there. Then that means b is equal to negative 1. Plugging a is equal to 1, b is equal to negative 1 in the first equation. Okay, so we have 1 and negative 1, 4 minus 2, which is equal to 2. Okay, subtract that from 5, you get 3, so c is equal to 3. So the polynomial that has these three criteria, the second degree polynomial, that is the quadratic that has these three criteria, at that point, locally, it has a point on the curve, the point on the curve 2, 5. It has a slope at that point 2, 5, a slope of 3, that's the instantaneous rate of change, and its second derivative at that point is equal to 2. That tells us about the curvature called concavity, and we'll look at that geometrically a little bit later, okay, in the course, that concavity. But this tells us how fast the slope is changing as we continue moving along the curve. In other words, you know, how much curvature we find at that point. And the quadratic, which would have those characteristics at that point 2, 5, would be x squared minus x plus 3. That's where a is 1, b is negative 1, and c is equal to 3. Okay, now back to finding the second derivative, general power rule. Okay, we're taking the derivative of a derivative in this example here. So we take constant multiple rule, we take out the constant. So 5 halves, and then take the derivative of x to the negative 1 half. Well, that would be negative 1 half x to the negative 3 halves, right? Because negative 1 half minus 1 is negative 3 halves. And then the next term, we take out the 2/3 as a constant multiple, and the derivative of x to the negative 4/3 is negative 4/3 x to the negative 4/3 minus 1 is negative 7/3. Okay. So this step here shows that we've used the constant multiple rule as well as the sum rule to distribute the differential operator as well as the general power rule. So all the rules are applied in that step right there. And then if we were to clean this up, if we were to look at it in a solution manual, we would find an answer of probably something like, or maybe something like negative 5/4, and then we have x to the negative 3 halves. I can push that to the denominator as something like a square root of x cubed. Possibly it could be written that way. And the next term, we would have a minus 8/9. X to the negative 7/3 is the cube root of x to the 7th. So that's probably one potential way that the answer could be written in a solution key. How about this example? Let's see. Find f prime of x given that f of x is equal to, how about x plus root x to the power of 2? Okay. How do we find f prime of x? Okay. So we want to take the derivative of what we have here is a function of x raised to a power. Now, we cannot distribute the differential operator into this. Okay, it is not linear right now. Okay, it is in fact, is to the power of 2. Okay, so what we should do is we should use some algebra here to expand. Why? Because we want to get power function terms, if possible. Okay, so we're using a little bit of algebra, in order to apply the calculus. Okay, we don't yet have the rules that we need to take the derivative of this without using some algebra. Not yet. Okay, so here's what we're going to do. FOIL this out. X plus root x, okay, times x plus root x. FOIL that out. We'll get a combination of terms. So we get the derivative of, let's see, we'll have x squared plus we'll have x root x and another x root x. So 2x root x plus square root of x times square root of x. Well, that is x. Okay, now write this as a as power terms, right? Though the first one's already a power term, the last one's a power term as well, but the one in the middle we need to adjust by rules of exponents. X root x is x to the first times x to the 1/2, which is x to the 3/2, right? Add the exponents. So we have 2x to the 3/2 as the middle term, and then x to the first as the last term. We now have power functions as our terms. And we can distribute the differential operator, factor out the constant multiple, and we can apply the general power rule, right, in the next step. So on the first term, the derivative of x squared is 2x, or 2x to the first, right? General power rule. The next one, we have 2 times 3/2 x to the 1/2, right? Because subtracting 1 from 3/2, we get 1/2. And then the derivative of x to the first, okay, well, that's just 1x to the 0. In other words, that's just 1. Okay? We've used our rules in that step right there. Okay? And that's where I can look to grade term by term to see that you use the appropriate rules of differentiation for this section. We can clean this up. If we're looking up our answer somewhere, we have, let's see, 2x plus 3x to the 1/2, which can also be written as 3 root x, and then plus 1. Okay. So a couple of examples then that I've given you already, a few examples whereby using a little bit of algebra from the start, which at this point has the goal really of writing our expression as a sum or a difference of power functions. That's individual terms that are power function terms. Okay, using a little bit of algebra to get it written in that form, and then we can apply the general power rule, along with the constant multiple rule and the sum and difference rule as well. Okay, let's take a look at that exponential function now. Okay. Jump ahead here to the exponential function. Okay, so this is the specific rule that we're deriving here, and I have the derivation of it here in your notes for your interest. Okay, so the derivative of e to the x with respect to x is e to the x. Okay, that's the big takeaway here. That's what we want. The proof of that is done by looking at the limit definition of the derivative first in general for a function f of x equals a to the x. That's an exponential function such that it would be continuous. Okay, so that it would be then differentiable. Okay, in order for the derivative to exist, we require that the function is continuous. You will recall. Well, the function f of x equals a to the x is in fact only continuous, okay, for certain values of a. F of x equals a to the x, okay, is continuous. Okay, and in fact, it's specifically continuous on all real numbers, but it's continuous if a is greater than 0 and a is not equal to 1. Okay, so that would mean that we have the case where if a is greater than 1, we would have exponential growth. Okay, it would look like that, for instance, and this would be the point 0, 1, for example. Okay, it does have a horizontal asymptote here, y equals 0. And then we have the case of exponential decay as well. All right, so we have a function that goes out like that. Again, it would have a horizontal asymptote at y equals 0. It also crosses through the point 0, 1. This is the case where a is between 0 and 1. Why the funny business? Why not the other numbers? Well, what happens if a is equal to 0? Then you have the function f of x is equal to 0 to the x, but that's just f of x is equal to 0. What does that look like? It looks like the x-axis. It's just a flat line. Now that's fine. Okay, we can take the derivative of that. Okay, but the derivative of that isn't going to follow a rule of exponential functions so much as it's simply its slope is what? Its slope is just 0 because it's a constant function. That's also the case, by the way, in terms of the derivative, if a is equal to 1. Okay, if a is equal to 1, then f of x equals 1 to the x, but that's just y equals 1. Right? That's all that is. And so that would look like a line, horizontal line, y equals 1 if the case was that the base was equal to 1, and then, well, the slope of that would equal 0, so the derivative would just be 0. So these are both constants, right? The exponential function reduces to a constant if a is either 0 or 1. Okay, and so it's not growth and it's not decay if a is 0 or 1. In fact, it's constant, and the derivative would therefore just be 0 in either of those cases. Well, what about if a is negative? Okay, is the other thing to consider. If a is less than 0, okay, then the issue that we're going to run into is that the function is therefore not going to be continuous. So take for example, if a is equal to negative 2, okay, that is if the function is f of x is equal to negative 2 to the power of x, okay, so you'll be fine at some locations, like for instance if x is equal to 0, y would equal 1. Negative 2 to the power of 0 is equal to 1. If x is equal to 1, you're going to get y is equal to negative 2, and that would be fine. But in between those two, you would have 1/2. What happens when x is equal to 1/2? At x is equal to 1/2, the y value would be the square root of negative 2, okay? And that is not a real number. So as a result of that, if we were to try to plot this, okay, we have a point at 0, 1, for instance, that we could plot, and then we have this point that's out here at 1, negative 2, that somehow we get to, but in between where x is equal to 1/2, what do we have? The function is completely missing here. There is no point here. So really, there's a discontinuity. Okay, and therefore, f prime of 1/2 itself does not exist for the function f of x equals negative 2 to the power of x, right? In fact, as it turns out, if the base were allowed to be negative, we get a whole host of problems of discontinuities going on. Okay, having to do with the density of real numbers, that you're going to have a point next to a location where there's not a point, and that's going to show up in so many places. It is so miserably full of discontinuities that the derivative is very challenging to define for such a function. So we stick with these two cases here where it's nice and continuous, and by the way, I would mention smooth, nice curves where the derivative exists. There's no corners, no cusps, no vertical asymptotes to deal with, no discontinuities at all throughout the entire domain. Okay, so these are the exponential functions that geometrically we see should have derivatives. We should be able to, any point on the curve, affix a tangent line and establish the slope of that tangent line, and it should be defined as a real number. There would be no points where we would have an infinite slope or an undefined slope. Okay, so we know that the derivative has to exist geometrically to this thing. So the idea is, well, how do we find it? Well, let's apply the limit definition of the derivative. F of x plus h minus f of x over h. Use that difference quotient. We get something like this. A to the x plus h minus a to the x over h. We can factor out a to the x by rules of exponents from this. A to the x. Now, notice here, we're taking the limit as h is going to 0, not x, right? So h is the thing that is varying right now. H is in motion. It's not x that is moving. X is standing still while h is moving. As a result of that, a to the x is constant right now. It's constant with respect to the limit that's being run. The limit is not x moving anywhere. The limit is about h is the thing that is moving. So a to the x is constant with respect to this limit. Therefore, a to the x can be factored out. Okay? But can be factored out as a constant multiple. All right? By the rules of limits. We can factor out a constant from a limit. And a to the x is constant with respect to the variable in the limit. And that leaves us with this expression. How do we evaluate that? If you plug 0 in for h, you get 1 minus 1 over 0. In other words, 0 over 0. This is suggesting that there is a removable discontinuity here. But the numerator is not a polynomial. So we can't factor out the discontinuity like we could with polynomials. We have another issue to deal with here. This is exponential instead. But what we're finding is that the derivative of a to the x, has a to the x itself within its own derivative. The derivative of a to the x is a to the x times some quantity, and that quantity is whatever this limit happens to equal. And this limit will equal different values depending on what a is equal to, it turns out. And that's for us to take a look at further in a future section. But what this does establish for us right here is that an exponential function that is continuous and smooth, that is the growth and decay exponential models that show up so much in the natural sciences in so many places, those growth and decay models, okay, their derivatives are proportional to the function itself. Okay? So there's a constant of proportionality that is being multiplied by the exponential function in its derivative. Now, it turns out that there is one particular exponential function such that the constant of proportionality happens to equal 1. All right? And that is that the derivative of some exponential is exactly just equal to the exponential itself. As long as c is equal to 1, then the derivative of a to the x would be a to the x. That's only true for one particular exponential function, and it would be the exponential such that this limit right here is equal to 1. If this limit is equal to 1, you have an exponential function with a very interesting property, that function is equal to its own derivative. So let's take a closer look at that limit. Now, the number e is defined this way. The limit as n goes to infinity of 1 plus 1 over n to the power of n. One of the first places you may have seen that number is in doing compounding interest, when dealing with that in an algebra class, as the base for when you are compounding continuously. That's if you are compounding all the time. Remember, compounded interest is where you accrue interest on a principal, and then the interest is reinvested periodically into the account so that the next interest compound would include interest on the interest as well as the principal. That's compounding. Well, if you're compounding all the time, we say that is compounding continuously. Okay? And this is derived, we can demonstrate how this is derived from that formula. So this is the definition for e. It comes out to be, it's an irrational number. That is one that the decimal sequence never repeats and never terminates. Okay? It can never be expressed as a fraction, not exactly. It can only be approximated by a fraction and only approximated by decimals. It is an irrational number, but has a very important property in that it is a natural base for exponential growth and decay models for phenomena that are growing or decaying continuously. That is all the time evolving and changing, which is exactly what natural and biological and ecological systems will do, and economical systems as well. Okay, they're always changing continuously. Okay, so this base e is a very commonly chosen base for when we're dealing with naturally growing or naturally decaying systems. And as it turns out in the calculus world, it is a preferred base because e, it turns out, is exactly that number that in our definition of the derivative of the exponential, it's exactly that base such that that limit would have equaled 1. In other words, it turns out that the derivative of e to the x is exactly equal to e to the x. So this base e is a really interesting number in that it shows up in so many applications for us. Interesting in that it's an irrational number, which is an interesting phenomenon for numbers like pi and the square root of 2, for example, and their geometric applications as well. But it's also very interesting in the calculus world in that the derivative of e to the x is exactly equal to e to the x. Now, the proof of the fact that this limit is equal to 1 specifically, okay, I show right here. You take the definition of e that we had from just above, from the compounding interest, and you do a change of variables to make this look more like our definition of the derivative. You change from the n going to infinity to h going to 0 by this choice. If we let h equal 1 over n, then notice that as n goes to infinity, then 1 over n would go to 0. So as n goes to infinity, it's the same as h going to 0. Right? The limit as h goes to 0 of h is the same as the limit as n goes to infinity of 1 over n. So we can make this change of variables. We can replace 1 over n with h, allowing us to replace n to infinity with h to 0. And then this n in the exponent is equal to 1 over h. Right? It's the same statement again. So we've rewritten the definition of e in this form. Now what do? Well, you can raise both sides to the power of h, so we do that, but now we've moved h to the left side of the equation, so we should also put the limit in front, since that is now a function of h. So the limit on the left is equal to the limit on the right. Now we can distribute the limit term by term. The limit of 1 is just 1. And the limit of h, as h goes to 0, we leave that right here. And that would equal 0 by itself, but we're actually going to do something different in a moment. So we have the limit as h goes to 0 of 1, well, that's just 1. And then we say, well, let's just subtract that from the other side as a constant. So we've moved the 1 to the other side. Now we just introduce dividing both sides by h. Why? Because this was the expression that we were trying to find the limit of. We have e to the h minus 1, we have limit as h goes to 0. If we divide this by h, we get exactly our expression. Okay? So we divide both sides by h, and now the limit on the left, the one we were trying to evaluate, must equal the limit on the right. We remove the discontinuity on the right, we have a limit of a constant that equals 1, and that proves it. It proves that specifically by the way that e is defined, that it turns out that e is exactly that number such that the constant of proportionality, when you take the derivative of an exponential, that constant of proportionality happens to equal 1 when the base happens to be that natural growth constant e. And that's your proof that the derivative of e to the x is equal to e to the x. And in the future, we'll prove more generally what would the constant have been if it were a different base. Like, what about the derivative of 2 to the x, or 5 to the x, or negative 1/3, or 1/3 to the x, I should say. Okay, for example. Then what would have been the constant of proportionality in those cases? And we'll find out in the future. Okay, so we have reached an important conclusion here then about this exponential function, f of x equals e to the x. Okay, and now let's go ahead and let's find some derivatives. Okay, find f prime of x if, let's say, f of x is equal to 3e to the x plus 10x. How about that? So f prime of x is the derivative of 3e to the x plus 10x. We can take the derivative term by term. And then we have constant multiple rule here. Then we have the derivative of e to the x. And then here we have constant multiple. And then we have the derivative of x. So we have the derivative of e to the x equals e to the x. We have that rule there. Okay, so this first term is just 3e to the x. And then the second term, we have 10 times the derivative of x, but the derivative of x is 1. So the answer is 3e to the x plus 10. Okay. Okay, let's try another one. find f prime of x if f of x equals 7x squared minus x to the negative 1 plus the fifth root of x plus 2/5 e to the x. Right, a variety of terms there. We have polynomial term, right? A rational term here. We have a radical term here, and we have a base e exponential term. And we do not need to use the limit definition of the derivative to do this, right? F prime of x, okay? We have the derivative of, let's write these as power terms when we can. So this is x to the 1/5. Now this term is not a power function, right? This is an exponential, base e. So we're not going to rewrite that one. We'll leave it as an exponential. And then we have here what? A constant multiple rule. We have 7 and then times 2x minus general power rule here on x to the negative 1 is negative 1x to the negative 2 plus general power rule 1/5 x to the negative 4/5. 1/5 minus 1 is negative 4/5 plus 2/5, and then the derivative of e to the x, which is just e to the x. Right? Derivative of e to the x is e to the x. All right, and then so this line right here shows all the rules. Okay, it shows all the rules that we have applied: constant multiple rules, general power rules, the derivative of e to the x, the sum and difference rules that allowed us to distribute the differential operator, all contained within that step. As far as a simplification, this is 14x plus 1 over x squared plus 1 over 5, let's say 5th root of x to the 4th, or just x to the 4/5, and then plus 2e to the x over 5. So that could be one way that we have it written if we looked at like a solution key, for example. All right. Applications. Back to our notes. All right, here we are. Okay. Finding tangent lines and normal lines to a function at a point. Okay, we already know about the tangent line. Now we don't need the limit definition of the derivative in order to find its slope. Okay. Tangent and normal lines, okay, to a curve. So to y equals f of x at x is equal to a. So that means at the point a, f of a. So take a look at the geometry here. If we have a curve with a point, right, where x is equal to a, so y is equal to f of a, so this is the point with coordinates a, f of a. Well, we have a tangent line to the curve. Okay, there's a tangent line to the curve, as we've seen previously, and then there is also, for us to consider, a normal line to the curve, and the normal line is also going to fix to the point, okay, to the same point on the curve, and geometrically the normal line is defined so that it is perpendicular to the tangent line, so at a 90-degree angle. Okay, so let's recall algebraically how to relate the slopes of lines that are perpendicular. Okay, the tangent line has a slope that is going to equal f prime of a. All right, the normal line, given that it is perpendicular, would therefore have a slope that is the negative reciprocal of the slope of the tangent line. That is the slope of the normal line. Okay, I'll call this m t, about the slope of the tangent line. This can be mn, the slope of the normal line, is going to be negative 1 over f prime of a. Okay? So recall, first, how about parallel lines? Parallel lines, okay, are lines that have the same slope, okay, but do not intersect. Now, a line, by the way, two lines that have the same slope and intersect would in fact be the same line as each other. And if they're the same line as each other, they're not parallel. So that's why I make that note. So parallel lines have the same slope, okay? But perpendicular lines, okay, the perpendicular lines that have, say, slopes m1 and m2, okay, the slopes relate this way. They are negative reciprocals of each other. Any one of the two slopes is the reciprocal of the other slope and the opposite sign of the other slope. Okay? Negative reciprocals of each other. Negative reciprocals of each other. So the normal line, okay, affixes to the same point on the curve that the tangent line does, but the normal line is perpendicular to the tangent line, and therefore at that instant on the curve, the normal line is in fact perpendicular to the curve itself. Now, notice geometrically, this will be helpful as you move ahead in your calculus courses as well. As we move the point, the tangent line also moves, right? Faces in a different direction, okay? But also the normal line will change its direction. The normal line is always going to face outward from the direction of travel. The normal line will always be perpendicular or orthogonal to the direction of travel along the curve itself. That has a lot of important geometric applications in a variety of places, such as engineering, okay, and physics. Okay, that's very helpful. But that's how a normal line is defined, okay, geometrically. Okay, a little more here in the notes. Okay, all right, I give you an example here. Find the equations of the tangent line and the normal line. Okay, let's do something like that. And then an application. The other application down here is velocity and acceleration. We'll take a look at that in a moment as well. All right, so let's try a tangent line, normal line example that isn't in your notes. Okay, let's see. Find the equation of A, the tangent line, okay, and B, the normal line, to f of x equals e to the x plus 5x at the point 0, 1. Okay? Now, in these exercises, I think it's helpful to, in fact, verify this is actually a point on that curve. It has to be geometrically, it should be. We expect that the point we're interested in is on the tangent line, on the normal line, and on the curve itself. Okay? So let's just verify our point. So if we go to the function, we get f of 0 equals e to the 0 plus 5 times 0, and that just equals what? 1 plus 0, which is 1. So we verify that, yes, the point 0, 1, that is on the function itself. Without having to graph this function to find the tangent line and normal line that way, we can at least have, sort of in our mind's eye, we can have a picture of this is how it's going to work out geometrically. As long as this function is continuous and differentiable when x is equal to 0, then we know geometrically that both of these features will exist. It requires that the derivative exists at that point. The function must be continuous and differentiable at 0. Is it? Well, the function is built up out of the sum of an exponential, which is continuous for all real numbers, and a polynomial, which is continuous for all real numbers. And hence, both of those terms are differentiable for all real numbers, which includes 0, so this function is differentiable at 0. We know that it is smooth at 0. Differentiable at 0. And therefore, geometrically, these features must exist for this function at that point. In fact, we could do the same thing for any point that we could find along this curve. We're just being asked to do it for this point right now. Okay, so let's start with the tangent line. Okay, the tangent line. All right, the tangent line at the point 0, 1 has a slope m, okay, call it mt, the slope of the tangent line, which is equal to f prime of 0. Right? We evaluate the derivative of this function and then we input the 0. Okay? Now we don't have to use the limit definition. What instead I'll do is I'll find the derivative of the function as a function itself, right? So the function as a derivative, and then I'll plug in the fixed value. Not the other way around, by the way. If we were to plug 0 in first, watch out, right? If you plug 0 into the function, you would get f of 0 equals 1. But if you had f of 0 is equal to 1, if you then tried to take the derivative of that, you're just going to get 0 every time, right? If you plug the number in before you take the derivative, you're always going to just cancel out and get 0. And that's not giving you true information. So instead, okay, take the derivative as a function first. Okay. Find f prime of x. Okay. Okay. Then you let x equals 2 in order to find out what f prime of 2 is equal to. Okay, and that's the process that we should follow. Okay, and then f prime of 2 would equal our slope, the slope of the tangent line, that is. Okay, but don't reverse this process. If you plug the number into the function and then take the derivative, right, you'll just take the derivative of a constant, it'll be 0, and that does not mean the slope is actually 0. So let's find the derivative first here. F prime of x is the derivative of e to the x plus 5. Okay, so we have the derivative of e to the x plus 5x. Sorry, that's what I meant to say. Okay, so we have the derivative of e to the x, well that's e to the x, and the derivative of 5x, well that is just 5. So here is f prime of x. This is our derivative as a function. So this is the slope for any value of x within its domain, so where this derivative exists, and its domain is all real numbers. So let's plug in... I don't know why I said x equals 2 over here. I'll go ahead and change that. Whatever x is equal to, then let x is equal to a, and then f prime of a is equal to the slope of the tangent line. That way it's more generalized. Okay, so in this case, we're finding f prime of 0, and f prime of 0 is what? E to the 0 plus 5, which is 1 plus 5, which is equal to 6. And so 6 would be the slope of the tangent line. Now the equation of a tangent line is y minus f of a equals f prime of a times x minus a. Right? That's a tangent line equation as we have seen previously. Okay, it's the point slope form of the equation of a line. Y minus y1 equals m times x minus x1 is what that is. Where the point that we have is a f of a. That's the point on the curve. And f prime of a is the slope. So let's plug in the quantities we know, right? F of a, that's f of 0 in this case. F of 0 is equal to 1. So we have y minus 1 equals, now the slope, okay, the slope is 6. And then we have x minus a is equal to 0, right? So we had, again, in this case, a f of a, okay, is the point 0, 1. And the slope we have, okay, was f prime of a, or f prime of 0, right? And that was equal to 6. So we have a point, we have a slope. Here's our equation. Okay, we can just box that answer right there. Okay, say that's our equation of the tangent line, and we're done. You can also put it into another form, like slope-intercept form. So y equals 6x plus 1. Okay, that would be a slope-intercept form of the equation right there. Okay, so there's our tangent line equation for part A. Okay, either one of these, y equals 6x plus 1, that's the tangent line to the curve at the point 0, 1. And then we want to find the normal line now. So we'll do that. Part B. the normal line to f of x at 0, 1. And again, the normal line is going to have the point a f of a, again, is going to be on that line. And the slope, okay, the slope of the normal line, okay, is going to be negative 1 over the slope of the tangent line, the negative reciprocal of it. So our slope is going to be negative 1/6. So we have a point, we have a slope, we can write the equation of the normal line. Okay, so we have, I could write it formulaically. Y minus 4a is equal to, negative 1 over mt times x minus a. Okay, so we have, in other words, we have a point, we have a slope, right? So y minus 1 is equal to negative 1 over 6 times x minus 0. Okay, so there's the equation of the normal line. And that's fine. If we wanted to put this into a slope-intercept form, we could do that. Y equals negative 1/6 x plus 1 is what we would get if we try to put it in slope-intercept form. Okay, notice, you might notice then that both of these lines share the point 0, 1, right? If you plug x equals 0 into either of these equations, you get y is equal to 1, just as you would get from the original function. X equals 0, then y would equal 1. So they all have the same point. The slope of the tangent line, okay, is equal to the derivative evaluated at the fixed point. And it is perpendicular, the tangent line is perpendicular to the normal line because, right, because we took the negative reciprocal of the slope. Okay, writing it in the point-slope form is highly recommended. The slope-intercept form is nice and clean and can show up in answer keys, but doesn't really demonstrate what you actually did to get there. For instance, this particular exercise, you have a +1 here and a +1 here. That's actually really dependent on the fact that we happened to be choosing 0 as this input. If that input was not 0, we wouldn't have had the same y-intercept for both of these. The only reason the y-intercept is equal to 1 in both cases is really because the point itself was already a y-intercept of the curve. So I urge some caution here, that you're not taking this equation and just replacing 6 with negative 1/6 and calling it a day. You'll find out, more often than not, just replacing the slope with a negative reciprocal in this equation here would be the incorrect answer. Okay? It is more correct, though, if you were to replace the slope of the tangent line in the point-slope form by the slope of the normal line. Then that would be correct. So I urge you to stick with point-slope form, but be aware that you might be asked to enter your answer. For instance, in WebAssign, they might want to enter your answer as a slope-intercept form. That's possible. And if you're looking up your solution in a solution key somewhere in the back of the book, you might find the answer written in slope-intercept form. Okay, so I have one more application here to look at. And that is taking this idea of higher derivatives that we've talked about previously. That is taking the derivative of a derivative, for example, and putting it to the application of velocity and acceleration. So let's do an example like that. You have one worked out here. I'll give you another one now. Find, let's see, A, the velocity, and B, I'll do it this way, B, the acceleration, okay, of the particle. So I have a particle that's going to be moving along a function. Find the velocity and acceleration at t is equal to 0 seconds, and let's say at t is equal to 5 seconds. Okay. Also, find C when the object is at rest. Okay, that is when it has stopped. Okay. Now, in order for an object to be at rest, according to what we're looking at here, that means it is not moving. And if it is not moving at rest, that means that the velocity at that time is equal to 0. Okay? And in this case, this will be 0 feet per second. I'll put it in feet, the distance in feet. Okay? So it's at rest if the velocity happens to be 0. For any value of t such that the velocity is 0, the particle would be at rest. Okay? And I'll give you a position function. Given the position function s of t equals t cubed minus 9/2 t squared plus 6t plus 4. Okay? Given that function, okay, is a position function okay, of a particle where t is time measured in seconds and s is distance measured in feet. Okay, distance from some observation point, for example. Okay, so we're asked to do 3 things here. Find the velocity at time is 0 and time is 5. Find the acceleration at time is 0 and time is 5. And determine at what times the object is standing still. When is the object at rest? Which is application of a velocity function. We're given a position function here. Okay. Here we go. Part A. Okay. Velocity. Okay. To paraphrase, we are asked to find v of 0 and v of 5. What's the velocity at 0 seconds? What's the velocity at 5 seconds? And to do so, we follow the same process where we're going to find the derivative as a function first, and then we're going to input the value of the constant, the input value of the constant, in order to evaluate the derivative there. Okay. Find the derivative as a function and then plug in the number. Okay. And we'll recall that v prime of wrong way, right? V of t, the velocity function, is the first derivative of position. Okay, so v of t is equal to the derivative of the position function. So d over dt, Leibniz notation, t cubed minus 9/2 t squared plus 6t plus 4. We have a polynomial here, set of power functions. Distribute the differential operator and use our rules. The derivative of t cubed is 3t squared. Then we have constant multiple rule. We can pull out the negative 9/2. The derivative of t squared is 2 times t, okay, or 2t to the first, right? Plus 6 times 1t to the 0, which is just 1. And then the derivative of 4, well, that's just 0. Okay, but now we're not done with the exercise yet. So we're not just asked to find the derivative and be done with it. Okay, and we found the derivative because it was an application here, right? The velocity function is the derivative of position. Okay, but now in fact we want to evaluate the velocity function at 0 and 5. So I'm going to go ahead and clean this up a little bit in preparation for doing that. Okay, I'll make it a little easier. 3t squared minus 9t plus 6. This is our velocity function for all values of t in the domain. Okay. I'll give us a domain here. I'll say t is greater or equal to 0, in fact. Okay. All right, so here's v of t. Now, what is v of 0? Okay, v of 0 is, well, 6. And that would be measured in feet per second. Okay, interpretation. What's our interpretation of that? Okay. The particle's velocity t equals 0 seconds is positive 6 feet per second. So considering that the velocity is a positive number, right? Notice that v of 0 is greater than 0, right? So we can think that this object is moving probably to the right. If we were to plot it on a number line, we would think it's going to the right. Okay, moving to the right at the instant that t is equal to 0. Remember, so this is an instantaneous velocity. So we're looking at a photograph of this particle in motion, but we're adding that that component, that dynamic component of seeing how it is actually moving at the instant that we snap the photograph. It is moving to the right at 6 feet per second at that instant. Okay? And I know it's moving to the right because we have a positive velocity here. Okay, that's relative to the observer. Whatever direction we say is the positive direction, that's the direction it happens to be moving in. So that's v of 0. And what about v of 5? V of 5 would be 3 times 25, right? 5 squared is 25, minus 9 times 5 plus 6. And that is, let's see, 75 minus 45 plus 6, which is 36. Okay, so we have v of 5 equals 36 feet per second. So similarly, v of 5 is greater than 0. So we interpret that as saying that it is traveling to the right, but it's now moving faster, right? A faster velocity. Okay? So the particle's velocity is 36 feet per second. Okay. At t equals 5 seconds. So it is now moving faster than it was at 0. Was it increasing in velocity the entire time? Is that what happened? How would we know? Do we think that it just continued to increase continuously? Okay, along this interval from 0 to 5 seconds. How could we know? We could take a look at the acceleration function to see if that indicates to us whether there was it may be a difference between accelerating versus decelerating for this particle. Okay, was the velocity growing or was the velocity decaying? Okay, over certain intervals. Let's take a look at the acceleration function now. That's part B. Okay, the acceleration, okay, is the derivative of velocity. Right? And we're going to find the acceleration at time 0 and the acceleration at time 5 as well. We recall the acceleration function is the first derivative of velocity. It's the time rate of change of the velocity, which is the same as then the second derivative of position. Okay, second derivative of position. So this is a higher derivative. Okay, so we're going to find the acceleration by taking the derivative of velocity then, since we already have the velocity function. So we're taking the derivative with respect to t of 3t squared minus 9t plus 6. 3t squared minus 9t plus 6. And that gives us 3 times 2t minus 9 times 1 plus 0. So a of t is equal to 6t minus 9. Here is our acceleration function. Okay? Now a is being measured in feet per second squared, by the way. Right? It's a time rate of change of feet per second. Okay, so feet per second per second. Okay, let's find a of 0 and a of 5. So a of 0 is equal to negative 9. What does that tell us about the particle? The particle is doing what at time t equals 0? It is decelerating. It is decelerating at a rate of, let's see, at 9 feet per second squared. Notice I have absorbed the negative into the word decelerating here. I'm saying it's changing its speed in the opposite, okay, in the opposite direction of its travel. So while the object is moving to the right, the amount it's moving to the right is becoming less and less. In other words, the acceleration is opposite of the direction that it is currently traveling. That is a deceleration. Okay. Consider if the object was moving to the left, let's say 60 miles per hour, but moving to the left, its velocity would be negative 60 miles per hour, for example. What would deceleration look like if it were moving to the left? Okay. Well, it would look like that the velocity is getting less and less. In other words, again, if the velocity is getting smaller and smaller in magnitude, that indicates deceleration. So you have that the object's acceleration is opposite in direction of the velocity when you have a deceleration going on. Okay, so a of 0 is equal to negative 9 feet per second squared. An interpretation of that is it is decelerating at 9 feet per second squared, or you could say it's accelerating at negative 9 feet per second squared as well. So that seems to indicate, now again, earlier I asked, do we think this object, which was going 6 feet per second at 0 times 0, was later going faster at 5? Was it accelerating the entire time? Was it going faster and faster from 6 to 36 just by looking at those two values alone? Doesn't tell the whole story. In fact, what was happening right here, while it was moving at 6 feet per second to the right, it wasn't starting to go faster. It was not accelerating. It was decelerating at that time. So this object was actually slowing down at this instant. Slowing down. It was moving at 6 feet per second, but getting slower. That means it must have, at some point, changed from slowing down to speeding back up again in order to eventually get to 36 feet per second. All right, let's continue here. What is a of 5 going to be? A of 5 would be 6 times 5. Okay, the particle is decelerating at 9 feet per second squared at t is equal to 0 seconds. So I'll complete that statement. A of 5, 6 times 5 minus 9 is equal to what, 30 minus 9, which is 21 feet per second squared. Okay, so that's our A of 5. So now what's happening? So now the particle is truly accelerating at 21 feet per second, or 21 feet per second squared at t equals 5 seconds. So now the object is accelerating at a faster rate. In which direction was it traveling at 5 seconds? It was moving to the right. So it is now, at that instant, it is traveling at 36 feet per second to the right. At that instant, it is also accelerating. So we can predict that in another interval of time, a half a second later, a second later maybe, okay, we predict that it'll be going even faster to the right than 36 feet per second squared. Than 36 feet per second, that is. Okay, so it will be going even faster. Okay, so now we've got A and B done. Now C. Find when the object is at rest. And we should interpret at rest as the velocity is 0. Just as we can interpret, let's say, with a height function, if we were given the height of an object, we know that the object hits the ground, let's say, when the height is equal to 0. Well, we know that an object is at rest if the velocity is equal to 0. So, object at rest. At rest, if the velocity function is equal to 0. Okay, so let's solve for that. Well, the velocity function was the quadratic 3t squared minus 9t plus 6. Okay, chosen because it has good numbers in it to make this work. So we're going to set that equal to 0, okay, and solve this equation. It is quadratic. We can factor out a 3. It leaves t squared minus 3t plus 2 equal to 0. And this factors real nicely, so we don't need any quadratic formulas for this case. T minus 1, t minus 2, okay, here we go. So when is the velocity function equal to 0? Okay, v of t is equal to 0 when, what, t is equal to 1 and t is equal to 2. T equals 1 and t equals 2 seconds. So what is happening at t equals 1 and t equals 2 seconds? We're saying that v of 1 would equal 0 and v of 2 is equal to 0 as well. Okay. The particle is standing still. That is, the particle is at rest. Okay. Yeah, let's go when. When t equals 1 second and when t equals 2 seconds. Okay, now we have just put together a pretty dynamic picture, all right, of the progression of this particle in motion, right? We're kind of putting together a film, a video of what this particle is doing. We know we know how to model its motion using the position function. Using algebra, with just basic function algebra, we know we can plug in a value of t and figure out where it is at, what position is at. Okay, but now with the use of calculus, we can do much more than that. It looks like when t is equal to 0, the object is moving to the right at 6 feet per second. Also, at time is equal to 0, it is decelerating. It is slowing down at that instant. Okay, you can put this in motion. It is slowing down while moving to the right. And it slows down until t equals 1 second. What happens when t is equal to 1? The velocity has gone from 6 down to 0. So it is now, so if you can imagine, it's like the progression of this thing, right? It's moving to the right, it slows down, right? So at t equals 0, it's moving to the right at 6 feet per second. It slows down until it is stalled out. It's now at rest. It is standing still. It's been moving to the right the entire time. Okay, so we have the object moves down and then it slows and then it stops at some point, right, at t equals 1. Okay, and then what happens? Right, we can look a little further into the velocity function and see, like if we graph this velocity function, we see as a quadratic. This is a upwards facing parabola. It crosses at t equals 1 and t equals 2. It opens up. So the velocity function is less than 0. It's less than 0 between 1 second and 2 seconds. The velocity will be negative between 1 second and 2 seconds. That means after t equals 1, the object is going to start moving to the left, but we know that it comes back to rest again. We know that it has to come back to being at rest when t is equal to 2. So it moved to the right initially, it slowed down to be at rest, and then it moved to the left. Okay, if we're looking at this on our line, the object maybe started here, it moved to the right, it stopped, it turned around, it started moving back to the left again. Okay, it moved to the left a bit, and then it stopped at t equals 2 seconds. And then after that, after t equals 2 seconds, the velocity became positive again, so the object started moving to the right again, and it continued moving to the right, okay, for the remainder of all time according to this model. Okay, and it was continuing to accelerate. Okay, so after it stopped the second time, it then started to accelerate in this direction, and it continued accelerating outward in this direction, moving towards the right. So the object moved towards the right, stopped, turned around, stopped at some point, and then turned around again and moved off to the right, then continued to accelerate out to the right forever. Okay, so that's kind of the putting this particle in motion using the calculus to try to analyze this. And we'll be doing more of that type of stuff as we move ahead in the course. Okay. All right, questions such as this come under the title of rectilinear motion. So it's motion along a line. You can envision it like this, like is it a particle that's moving maybe back and forth along a line, and that line can even be a curve. But rectilinear motion, position function, velocity function, acceleration function, for example. And with that, that is all for this section. So you have a lot to look at and think about with this section. You can let me know if you have any questions, and good luck with the homework. Take care.